everyone. I'm Jacob Pardue. I'm with Group 2 with Matthew and Mia as well, and I'm going to be talking about the experiment that we'll be doing next week, which is the Clapeyron experiment. So our goals of this would be to determine the latent heat of evaporation using water and the Clapeyron equation as well. And we're going to do this over a range of pressures and temperatures, and I'll go into a little more detail how we'll be doing that later on. And then we're going to be verifying them as well, verifying these values with our steam tables that we've gotten in thermodynamics. So first things first, what is latent heat? What does it mean? And what is the Clapeyron equation? What does that mean as well? So latent heat is basically the energy absorbed by a thermodynamic system during an isothermal process. So it means basically from here to here, your temperature stays constant. It's the energy that's released during that process. So while you're boiling, how much energy will it take to boil, basically? This is the Clapeyron equation right here, and you can go ahead next. This is the latent heat of evaporation term, so HF, and it's basically an equation that relates the properties of the thermodynamic properties. Right? So things like your pressure and your temperature and your specific volume, they can all be related in this equation. You can also use the ideal gas equation as well, since it is in a vapor state. And what is it used for? What is its applications? So it's used in a lot of different industries: aerospace, nuclear power plants, meteorology, just to name a few. There's much more. And I've got a picture up here of a rocket test stand. So why do I have a picture of a rocket test stand up there? It's because that's actually a huge component when it comes to water-cooled deflector or plume deflectors. So last semester I actually took rocket propulsion, and we did a project on designing a rocket plume deflector. And latent heat was used to find how much water should be sent through the J-curve, it's called the J-curve right here, to basically make sure your J-curve doesn't get destroyed. So this is the apparatus that we're going to be using, and there's a list of the different things that we will be using, all numbered, and then this picture is also correlated to those numbers. So you see we've got the the flask with the rubber stopper. It's going to be holding our water. The hot plate underneath it is going to be heating it up. Our thermocouple will be measuring its temperature. And there's also going to be a pressure transducer seen here at 4. Mechanical pressure gauge, so we can see the actual pressure that is in the flask. An air bleed valve, that's basically so we don't blow up the flask when we relieve the pressure. And a pump to get the air out, of course, to create vacuums. Water reservoir, I'm not too sure the physics behind why we would be using that, but we do have it. That's what we have here. And then the computer system, of course, to log the data. So, I'm sorry. Basically, what we'll be doing is we'll be heating this water, and we'll be taking measurements between 50 degrees Celsius and 100 degrees Celsius. So there's going to be a vacuum. We're going to start with a vacuum inside, and then gradually release the vacuum. And with that, the boiling temperature will go up as well. So with that, we can measure, using the Clapeyron equation, what our latent heat of vaporation, vaporization, is going to be. Here is a latent heat of vaporization versus temperature chart. Pretty standard, pulled it right off of Google. And we'll be testing around the 50 to 100 range right here. So we should be expecting around 2,500, or I'm sorry, about 2,300, 2,400. And we should be able to confirm that with our thermodynamic tables as well, as stated. And a few inaccuracies we might run into, of course, the thermocouple type K normally has around 0.5 to 2 degrees Celsius errors in it. The surrounding temperatures may mess with the results as well, so things like room temperature and body heat, and lack of a perfect vacuum. So we obviously can't pull a perfect vacuum in the flask itself, so that might lead to a little bit of error. And that's it. Any questions?